Assalamualaikum warahmatullahi wabarakatuh. My name is Aisyah Amirah binti Abdul Razak. I will present my thesis titled Enhanced Conductivity of Epoxy-Filled Carbon Black Conductive ink via green co-solvent technique. What is actually conductive ink? Conductive ink is an ink that results in a printed object which conducts electricity. The conductive ink consists of binder and filler, and mostly conductive ink is used in RFID tags, e-textile, and wearable electronics. Inks are reasonably priced, simple to manufacture, low viscosity, and have high stability, and the disadvantages are not 100% effective and have short shelf life at room temperature. Next, we use epoxy as a binder agent in the conductive ink. The advantages of epoxy are strong adhesive strength, low shrinkage, low cost, low dielectric content, and corrosion resistant. And the disadvantages is it cannot conduct electricity by itself, so we have to add filler to produce good conductive ink. Next, we use carbon black as a filler in this study. Since most polymers are naturally electrically insulting material and do not conduct electricity, in some applications, adding carbon black to the material matrix might result in the required performance, such as increase the conductivity. The advantages of carbon black are low cost, low flammability, high safety, and conduct electric well. The example of other pillar is nickel, aluminium, and graphene, but we use carbon black in this study because it is low in cost. Next, we use green mixing technique. By using green co-solvent, which are ethanol and distilled water, it decreases less harm from toxic chemical in the environment from this study. The advantages of green mixing technique is environmental friendly, toxic free, and less VOC will be released. The mixing technique of this study is most important stage in production of conductive ink because it properly distributes the filler particle throughout the polymer network. Carbon black filler have strong van der Waals forces that allow the formation of particle aggregation of carbon black. Due to the van der Waals forces between carbon black, co-solvents are commonly added to the resin to counteract it. Next, the screen printing method of conductive ink. It is the easiest and less expensive method due to its high impact strength, superior flexibility, and biocompatibility. PET substrate was chosen as a substrate for many different sorts of applications. Due to its outstanding qualities and mechanical flexibility under bending conditions, PET has been recognized as a good substrate choice in electronic devices and seems to be a promising option for the substrate material in the study. The problem statement of this study are epoxy alone cannot conduct electricity by itself, and the existing method used is non-environmental friendly solvent. The significance of this study is to identify the best loading of carbon black that have been used in the subsequent tests. This study also increased our knowledge of how carbon black enhance the electrical conductivity of conductive ink made of epoxy. The objective of this study are to prepare and characterize the various loading of carbon black filled epoxy conductive ink using FTIR and UV-based spectroscopy, and the second objective is to determine the conductivity properties on various loading of carbon black filled epoxy conductive ink via EIS and multimeter. The methodology of this study, the first one is to prepare and optimize of epoxy conductive ink filled carbon black, and the second one is characterization and conductivity testing. For the preparation of epoxy-filled carbon black conductive ink, In a beaker, 2 grams of epoxy resin was mixed with various loading of carbon black and co-solvent, which are ethanol and distilled water in the beaker. To ensure the filler mixed effectively into the matrix, the mixture was sonicated. Then, print screen was done. The liquid were poured into a glass-like mold and heated to 100 degrees Celsius for 1 hour. Then the sample were conditioned to the prior to further testing. For the characterization, the testing was done is FTIR and UV based, and for the conductivity testing, the testing is multimeter and electrochemical impedance spectroscopy or EIS. As you can see in the FTIR result, they are slightly changed when the various loading of carbon black added. For the pure epoxy, the peak at 3390 cm-1 were attributed to the material OH group. For the various loading of carbon black, peak in the range of 2965, 2920, and 2852 cm-1 were ascribed to the stretching CH vibration of the CH2 group of aromatic, the valence CH vibration of the epoxy, and the symmetrical CH stretching vibration of the CH3 functional group respectively. Compared to the spectra of epoxy, which is carbon black 0%, that have peaked at 2851 cm-1, CH3 stretching, 15% of carbon black peak more shift toward the higher wave number, which is 2852 cm-1. In the result of ultraviolet visible spectroscopy, low absorbance and no obvious UV-based absorption peak are characteristic of epoxy. The carbon black epoxy composite UV-based results show two stretch peaks between 310 and 370 nanometer. It is believed that CV having a conductivity characteristic due to the elongated double bond, which is associated by pi to pi star transition. The resulting pi to pi star transition are most likely to attribute to the increased surface area of the carbon compound exposed to the UV light. For the conductivity testing of multimeter, it can be seen based on the graph. The resistivity is inversely proportional to the conductivity. For 0% of carbon black to 15% of carbon black, the conductivity value increased steadily from 3.314 times 10 to the power of negative 4 Siemens per meter to 6.458 times 10 to the power of negative 4 Siemens per meter. For 20% of carbon black, the conductivity decreased to 2.4408 times 10 to the power of negative 4 Siemens per meter. This is because due to the agglomeration of carbon black at 20% of Cb. For the conductivity testing of multimeter, it can be seen based on the graph. The resistivity is inversely proportional to the conductivity. For 0% of carbon black to 15% of carbon black, the conductivity value increased steadily from 3.314 times 10 to the power of negative 4 Siemens per meter to 6.458 times 10 to the power of negative 4 Siemens per meter. For 20% of carbon black, the conductivity decreased to 2.4408 times 10 to the power of negative 4 Siemens per meter. This is because due to the agglomeration of carbon black at 20% of Cb. It can be concluded that the addition of various loading of carbon black filler result in the improvement of conductivity of the epoxy-filled carbon black. The result of electrical properties reveal that the incorporation of filler, which is carbon black, could improve simultaneously the conductivity in epoxy resin matrix composite. From this study, we can conclude that 15% of carbon black has been indicated as the optimal loading among the other loading. For the recommendation, the study can be improved by implementing the bond mix as a mixing technique to replace for the sonicator technique, which is to improve the conductivity of epoxy-filled carbon black. The sample of epoxy-filled carbon black can be uniformly mixed using the bond mix that can increase the conductivity of the carbon black sample and also prevent the agglomeration of particles with the epoxy.